Welcome back. Today's lecture in the chemistry series is chemical nomenclature, and in this particular lecture we're going to be focusing on simple compounds, primarily binary compounds. The next couple lectures will cover chemical nomenclature, and in each video we will discuss a different set of compounds and the various differences in how to name and in turn get the formula from the name of the compounds. So what's in a name? Why even bother learning chemical nomenclature, which is just a fancy way of saying naming chemicals? First and foremost, the name of the chemical tells you several things. First and foremost, it tells you what atoms are present. And that's really useful for chemists, especially beginner chemists, because if you don't know what's present, you don't know how it's going to react. You don't know what you're going to get out of a reaction. And you need to know what's there because there are a whole bunch of rules, for example, the law of conservation of mass, that requires you to know what goes into and comes out of a reaction. If you don't know what's in your materials beforehand, you have no idea what's going to come out of it. So what atoms are present is a great reason to know what the names of chemicals are. The second reason is the name gives clues as to the ratio of the atoms. Oh, excuse me, not as to, not at to. As to the ratio. Now, a lot of times it doesn't come out and tell you what the ratio is, unless it's a molecular compound, but I'm jumping ahead of myself. But the name of the atoms and the name of the compounds gives you a hint as to the ratio of the atoms there, and in turn it tells you what the probable ratios in the future might be once we get into chemical reactions. So we're going to start today's topic with binary compounds. A binary compound is a two-part compound. There are typically two atoms or sometimes two polyatomic ions, which that's a completely different lecture. Don't get hung up on that yet, but let's just start simple and say it's a two-atom compound or a two-element compound. That's a better way to say it, because it's not always just two atoms. There are three types of binary compounds. There's type 1, which is ionic, and in this case, type 1, the cation has only one charge. It will never have a different charge. So this is your group 1 and group 2 cations, and then a few of your group 13 cations. Type 2 binary are also ionic, and they are binary in that their cations can have more than one. Two plus charges, so it could be +1, it could be +2, it could be +6. And there's a special set of rules to name compounds that fall in this category. And your type 3 binary are by far the easiest. These are your covalent compounds, your molecular compounds. And these are basically anything on the right side of that magic stair step on your periodic table. Typically carbon, oxygen, silicon, selenium, elements like that form type 3 covalent compounds. And each of these three types of binary compounds has a set of rules applied to it. Type 1 and type 2 are similar, there's just a small caveat, and then type 3 uses a different system. And this, by using these different systems, it immediately tells you what type of molecule you're dealing with. It tells you, are you dealing with ionic or are you dealing with covalent? And as we remember talking about this in our bonding videos and our bonding learning about bonding, these two types of compounds behave differently, and this also helps chemists. So let's start with type 1. Once again, type 1 compounds are the ones that the cations have a constant charge. So you're looking at group 1, which is right here, group 2, boron and aluminum, and then that's really about it. The rest of the atoms tend to have multiple charges, or they're not cations. For example, these nonmetals typically form anions. And I've got two examples here. The way to name a type 1 compound, a type 1 binary, is basically just write first the cation, so Na, which if you'll look at your periodic table, which I've supplied here on the screen, Na is right here. That is sodium. Now you can't, it's not listed on this periodic table, but one you might be referring to, it'll be listed. Na is sodium. And the cation, even though it's an ion, you just write it as if it were the element. So sodium. Na is sodium. The second part of that compound is chlorine. Now, most of us have been around long enough to know that sodium chlorine is not a compound. NaCl is sodium chloride. That's table salt. For that to work, you first write the root of the element, which is, for chlorine, it's chlor. Usually it's the first syllable, the first couple syllables. And then you change the ene, the ine, or if it's oxygen, the second part of the word, into ide. So instead of sodium chlorine, this compound is sodium chloride. Let's take a look at the second one. The second one I have listed here is also a type 1. Magnesium is right next to sodium. It's in group 2. It always has a 2+ charge. Never changes. So when you're writing the name of magnesium, since it's the cation, the positive one, it's written first, and it's just written magnesium. You don't change anything. And then the second part is nitrogen. Nitrogen's your anion. Your nitrogen's over here in group 15. It has a -3 charge. That means it's an anion. And once again, first you write the root of the word, which in this case would be nit. Or actually, you add an R. And then you change the nitrogen, the O-gen, into nitride. And that's how you name type 1 compounds. Type 2 are a little different. Type 2 compounds are basically where your cation, your first element, is a transition metal, which is this big yellow block. It's group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and any of the other ones that butt up against this stair step. Gallium, germanium, tin, indium, titanium, lead, bismuth, these are all transition elements. Aluminum doesn't fall in this category because it just typically forms a +3 ion. But the rest of them, all these yellow elements right here, from group 3 up until the stair step, they can form different cations. They can form different cations because of this D block of orbitals. Remember, the D block is elements that have D electrons, and D electrons behave weirdly when it comes to bonding. So let's take a look at this first one. This is, well, actually both of them. These are both copper sulfide. If you were to write these elements according to the type 1 rules, it would just be copper sulfide. So let's go ahead and write both of them. Copper sulfide. However, if you take a look at them, you can tell they are different compounds. You've got CuS, which is a 1 atom of each, and then you've got Cu2S3, 2 atoms of copper to 3 atoms of sulfur. And this is where the difference is. Copper is one of those transition elements. It's one of those cations that can form multiple charges. And there's a method to solving this and figuring out what charge is what. But just for this slide, I'm going to show you what the proper name would be for these. This first one is copper 2. And I know it's copper 2 because your sulfur is typically a -2 ion, and there's only one copper, so that copper's got to have a -2 charge. This one down here is copper. Okay, I made a mistake when I was writing my formula. It's actually copper 1. Let's ignore this 3 right here. This should be copper 1. I wrote my formula wrong. I apologize, but it should be copper 1. So since there are 2 coppers to 1 sulfur, that means your copper's got to have a 1 charge. So let's take a look at that. Alright, so let's look at a compound. Let's look at one of my favorites, tungsten 6 sulfide. Now, how did I get to 6? That's a good question. There's a method to this, and you'll get used to it, and you can start taking shortcuts later. But to begin with, there's a method, and it takes a little paper and it takes a little time. But this is the way you should do it until you figure it out. First things first is you separate them. You write your 2 compounds separately. Be sure to include your subscript. And then you write their charges. Well, sulfur, you know, never changes. It's always -2. It's in group 16, so it always has that -2 charge. Tungsten, however, changes, so you don't know what the charge is. So how you figure that out is you take the number of atoms you have, so since I've got 3 atoms, and you multiply it by the charge. So I've got 3 times 2 is a -6. Okay? Now you look at how many atoms of tungsten you have, and since there's no number there, you assume 1. 1. So you've got 1 times some charge, which I'm going to represent as X in a box, equals +6, because remember, if this is ionic, it has to be balanced. So 1 times what gives you 6? Well, that would be 6. So for this particular compound, you would write it as tungsten 6. The Roman numeral tells you the charge of your cation. You only do that for compounds that have more than one cation, or excuse me, elements that have more than one cation. Just a general rule, if you do it for all transition metals, nobody's going to get mad at you, just until you figure out the little caveats. For example, silver is never anything but +1, but if you still write it as silver 1, no one's going to hold it against you. The last set is your covalent, or your molecular compounds, and those are compounds that only have nonmetals. That's this purple block up here on the right side of your stair step, and actually sometimes these green metalloids. So let's take a look at this. You don't have a cation and anion in this case. What you have is 2 compounds, or excuse me, 2 elements. You've got carbon and chlorine. You write the first word just as you would. So carbon's first, you just write carbon. You write the second word like you would if it was an anion, so you would change that to chloride. However, since it's not an ionic compound, you can't figure out the charges of the components. Instead, you've got to use a prefix. So, and the prefixes are your basic Greek prefixes. Mono, di, tri, tetra for 4, not quad. I know it's confusing, but for some reason chemists use tetra. So this would be carbon tetra chloride. Go ahead and take a second here and see if you can figure out what the next one would be. Now, if you've written something down, it should look like di, since there are 2 nitrogens, nitrogen, and then since there are 6 sulfurs, it's hexa sulfide. And I put it on the second line because I couldn't fit it in without shrinking my slide, and I apologize for that. But so this one would be dinitrogen hexasulfide. Once again, here are your prefixes. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, and really, octa's going to be the last one you're going to use. Very rarely do you ever use nona and deca, but they're still nice to know. Nona is 9 and deca is 10. So these are your chemical prefixes for your covalent compounds. And let's try one more practice with these. All right. Here is a compound. Let's go ahead and go with oh, not B. Sorry. Let's go with Alright, so here is a molecular compound. Phosphorus is nonmetal, oxygen is a nonmetal. So you know it's a molecular compound. So how you would fill this one out is, since there are 2 phosphorus, it's written first, it's diphosphorus. And then since there are 3 oxygens and it's written second, trioxide. Now there is one small caveat. For example, in one we're all familiar with, carbon dioxide and carbon monoxide. If your first element is a 1, you don't include the mono. If your second element is a 1, you include the mono. So this is carbon dioxide and carbon monoxide. So if you'll notice, both of these only have 1 carbon. I didn't include the mono in the front. You don't have to do that. Once again, nobody'd get mad at you if you did until you figured out the system, but in your later chemistry courses, you're going to have to know not to include that mono. That concludes our intro to simple compounds. The next video will be your more complex compounds, starting with, I believe, acids and polyatomics, and then we'll move into figuring out formulas from the name. See you next time.